first test shows how fault current and energy is limited by rapid fuse link operation. .600-amp fuse links are in series with 200-amp fuse links, protecting a cable which is short-circuited at the extreme end. The fault level is 40 MVA, which is 38,500 amps at 600 volts. The flashing lights indicated switch on. The oscillograms show that the current is rapidly cut off. There is no damage to the circuit. The test is now repeated with copper links replacing the fuse links. The fault level is the same as in the previous test. The only difference between this test and the previous test was that the fuse links were replaced by copper links. The circuit breaker was set to operate in 15 cycles. This slow-motion replay demonstrates how the build-up of heat in only 1/3 of a second is extremely intense, causing molten copper to be thrown in all directions. In the previous test, all this energy was limited and contained by the high rupturing capacity fuse links. The lower half of the bus bar system has been severely damaged. The energy that was let through in this test, due to the operating time of the backup device, was approximately 1,000 times greater than in the first test. The next test is with an internal short circuit at the fault level has been increased to 66,000 amps at 600 volts. The broken line represents the rise in fault current that would have occurred if the fuse link had not been fitted. This diagram shows the relative proportions of energy let through represented in amp squared seconds. The large box represents the energy flowing into a fault for just one cycle of fault current. The very much smaller box represents the energy let through by a GEC fuse link. The preceding test is now repeated with copper links in place of the HRC fuse links. The extremely high temperature reached and the destruction caused is due entirely to replacing the fuse links with copper links. All the other electrical and circuit conditions were exactly the same as in the preceding test. The damage and destruction is extensive. The center phase of the horizontal bus bars has collapsed completely, together with most of the outgoing bus bar copper work. If this was a main switchboard in a factory, it would have to be rebuilt, or more likely replaced, which would probably involve considerable loss of production. This next test shows how HRC fuse links limit electromagnetic stresses. The test rig is fitted with 400 amp fuse links protecting bus bars which are short-circuited at the lower end. The prospective fault current is 32,000 amps at 160 volts, which is equivalent to 33 MVA at 600 volts. The fuse links cut off the current, and the stresses between the bus bars cause only slight momentary deflection. The electromagnetic stresses between the bus bars are proportional to the square of the peak current. In this diagram, the large square represents the electromagnetic stress due to one peak of fault current. The very much smaller square represents the electromagnetic stress with HRC fuse links in circuit. The fuse links are now replaced by copper links, and the test is repeated with the backup circuit breaker set to operate after 5 cycles. The current has only been allowed to flow for 1/10 of a second, but considerable permanent distortion has occurred. The last 2 tests have shown how GEC HRC fuse links limit electromagnetic stresses when faults occur. These earlier tests demonstrated how GEC HRC fuse links limit fault energy, which can otherwise result in serious fire and explosion.